Master, when will humanity be able to colonize the Proxima Centauri system?
In many science fiction movies, humanity can reach the Proxima Centauri system, which is 4.2 light years away from Earth, within 2 or 300 years at most. But in reality, accomplishing such a feat is far more difficult than most people imagine. If you ask the scientists, they might talk about propulsion technology, energy, and distance. But in truth, this is neither purely a technological problem nor purely a scientific one. It is a challenge that combines technology, politics, and human nature.
Then let's start with technology. What technologies would be needed to colonize Proxima Centauri?
That question is still too broad. Let me break it down into two scenarios: fast arrival and slow arrival. Fast arrival means accelerating a spacecraft to a speed close to that of light, allowing humans to travel to Proxima Centauri within a single lifetime, perhaps even return. Slow arrival, on the other hand, gives up the pursuit of extreme speed. The destination can not be reached within a human lifetime, so the journey becomes a one-way trip and requires solving a great number of additional problems to succeed.
It sounds like fast arrival only requires solving the problem of speed.
Unfortunately, no. In fact, it is basically impossible.
I know it's impossible now, but what about the future?
The smartphone you're using, the computer on your desk, and intelligent vehicles are already among the finest products of human industry. Yet the fundamental physical principles required to create them were largely established over a century ago. What I'm saying is that theoretical physics is far ahead of applied physics. So the question becomes, based on the physical theories humanity currently understands, can we send people to Proxima Centauri in the foreseeable future? My answer is no.
Why?
The first problem is mass. Simply put, the faster and farther you want to travel, the more fuel you need. But fuel itself has mass. This creates a paradox. To accelerate, you need more fuel. But more fuel makes the spacecraft heavier and harder to accelerate. You may think that the problem is simply that our current fuels are too inefficient. Fine, let's boldly assume that some extremely efficient antimatter fuel exists, and that just 1 kilogram of it is enough for a round trip to Proxima Centauri. Now thrust is no longer the problem. Instead, we face a far more deadly issue, one that is rarely discussed: heat dissipation.
Heat dissipation.
Yes, the spacecraft's engines, reactors, and life support systems would generate enormous amounts of heat every second. If energy efficiency is low, heat isn't much of a problem. But suppose fuel efficiency improves by thousands or even millions of times compared to today's technology. The amount of heat produced in an instant would be terrifying. Without a way to remove that heat, the spacecraft would quickly overheat and destroy itself. The problem is that space contains almost no matter. As a result, heat can only be removed through radiation, which is notoriously inefficient. The current solution is to install enormous radiators, but radiators are heavy, fragile, and take up space. Worse still, larger radiators add more mass. More mass requires greater thrust. Greater thrust produces more heat, and more heat requires larger radiators. You see, a similar paradox appears once again. This is the fundamental limitation of rocket technology. After all, its basic principle is simply throwing part of itself backward continuously. Its upper limit is effectively built into the system from the very beginning.
Then what about new methods of propulsion? For example, solar sails?
The principle of a solar sail is simple. A huge reflective membrane captures radiation pressure from sunlight and uses it as thrust. This greatly reduces the need to carry fuel. The strengths and weaknesses of this concept are both obvious. The advantage is that you don't need fuel. The disadvantage is that the payload capacity is extremely limited.
Then couldn't I just carry less? 5 or 6 astronauts with only essential supplies. A payload of less than 100 tons doesn't sound particularly heavy.
For a solar sail, even a single human being is heavy. A 100-ton payload is far beyond practical limits. The main reason is that the thrust provided by solar radiation pressure is incredibly small. 1 square meter exposed to sunlight produces roughly 9 microtons of force. For a spacecraft weighing 100 tons, the sail would need an area of approximately 1 square kilometer just to generate around 10 newtons of thrust. At that point, the goal of fast arrival would still be impossible. Of course, you could increase the sail's area to generate more thrust. But don't forget, the sail itself also has mass. So according to current theoretical estimates, solar sails are unlikely to carry human passengers.
Master, I remember there was another concept for light sails. Using high-energy lasers fired from Earth as propulsion to greatly increase the spacecraft's initial speed.
Leaving aside the absurd amount of energy such acceleration would require, let's assume humanity has already mastered nearly unlimited energy. Even then, accelerating a light sail with laser would still remain something that exists only in theory. High-energy lasers shining on a light sail can indeed provide considerable thrust, but they're also more likely to burn the spacecraft apart. And even if humanity someday masters nearly unlimited energy and creates materials approaching absolute rigidity, the laser beam would still weaken over distance. In other words, the acceleration cannot last very long. Eventually, the spacecraft would still have to rely on the faint sunlight in space for propulsion.
Alright, according to what you're saying, light sail spacecraft are only suitable as small and lightweight probes?
Yes, suppose humanity wants to send a probe to the Proxima Centauri system. A light sail would be a good option. A probe weighing about e kilogram, with a sail unfolded to roughly the size of a basketball court, combined with initial acceleration from high-energy lasers, might be accelerated to 10% of the speed of light. In theory, it could reach Proxima Centauri in about half a century. Although that is still a very long time compared to a human lifespan. Compared with other proposals, it is the most realistic and the most likely to be achieved within the next 200 years.
Isn't there any theoretically feasible solution? The future is a long time away. As long as a theory exists, I believe future generations can gradually make it happen.
There's another very bold concept, the Bussard ramjet. This is a spacecraft that eats fuel while flying. The idea is to use an enormous magnetic field to scoop up hydrogen from interstellar space and use it for nuclear fusion propulsion. It sounds like a perfect solution to the fuel problem and would allow continuous long-term acceleration. However, space is simply too empty. The density of interstellar space is roughly 1 hydrogen atom per cubic centimeter. What does that mean? It means you are basically trying to catch air in a vacuum. To generate enough thrust, you would need an absurdly large intake, which in this case means an enormous magnetic field. A rough estimate suggests a magnetic field thousands to tens of thousands of kilometers in diameter, larger than an entire country. At that point, it is no longer a spacecraft, it is a mobile celestial structure.
Then let's just build it that big. Interstellar spacecraft are massive projects anyway.
Fine. Let's assume all of those problems are solved. The problem is that while you're collecting hydrogen, you're also colliding with hydrogen. That creates drag and slows the spacecraft down. Some studies suggest that, at realistic densities, the thrust generated by collecting hydrogen atoms may actually be less than the deceleration caused by hitting them. In reality, the harder you try to accelerate, the more you may end up slowing yourself down. And on top of that, such a spacecraft would still need to get rid of waste heat, which means building huge radiators. See, we're right back where we started.
Master, I've noticed that you haven't mentioned warp drives.
Yes, because warp drives are more like thought experiments than engineering projects with our current level of technology. The reason the previous spacecraft concept cannot be built today is mostly due to engineering challenges. A warp ship, however, faces the question of whether its physical foundations are even possible. Its core idea is indeed elegant. Compress space in front of the spacecraft and stretch space behind, allowing space itself to carry the spacecraft forward. It sounds like a perfect way to bypass the speed of light limit. But to achieve this, you would first need energy on at least the scale of Jupiter. And that's just the admission ticket. The difference in spacetime curvature between the front and back of the spacecraft would instantly tear it apart. To prevent that, you would need to create a warp bubble surrounding the spacecraft. That warp bubble itself cannot be affected by the surrounding spacetime. In other words, the physical laws inside the bubble cannot be influenced by the physical laws outside it. Do you see what that means? You are effectively creating a miniature universe with its own laws of physics. And if you really manage to create a warp bubble independent of our universe, you still face one final problem: information. To keep the spacecraft from being torn apart by the different spacetime conditions in front and behind it, you must block the influence of those external physical laws. But doing that means complete isolation from the outside world, which means you cannot observe anything outside the warp bubble. Which means once your spacecraft starts moving, it can never stop. Rather than a spacecraft, it would be a terrifying weapon. The people inside would not be explorers. They would be exiled, cast outside of time itself until the universe dies. That is why I say the warp drive is merely a thought experiment. In reality, it may simply never be possible.
It seems that landing in the Proxima Centauri system within a single human lifetime is much harder than I imagined. If getting there quickly is impossible, what about building a generation ship and taking a few thousand years?
The first problem facing a generation ship is its ecosystem. The minimum population required for sustainable human reproduction is roughly 1,000 people. That means creating a completely closed ecosystem capable of supporting 1,000 people. Such a system would probably need to operate for at least 1,000 years. That is not a spacecraft, it is a miniature Earth. Similar experiments have been attempted in history, such as closed ecological system projects, but they have largely failed. The reason is that ecosystems are far more complex than humans imagine. Any small mistake can be amplified indefinitely by time. Everything may look fine at first, then let's just build it that big. But after several decades, the entire system could collapse. But let us assume humanity eventually solves that problem many years from now. The next question is, can people endure it? Human beings are not naturally suited for long-term life in space. Gravity and radiation might eventually be solved through technology, but psychological and social problems are much harder to solve. Imagine being born aboard a spacecraft. Perhaps life is wonderful at first, but everything changes the moment you learn that Earth exists. You know that Earth has blue skies, white clouds, and vast open spaces. Yet none of those things belong to you. Your fate was decided by others long before you were born. Is that really fair? The first generation of crew members might tell their descendants that they are humanity's hope and that their mission is noble and grand. But after that generation dies, anxiety will begin to spread. Why should we spend our entire lives on this tiny spacecraft? The first generation volunteered for this mission. But did we? Behind us lie billions of our fellow humans and a warm, comfortable home. Ahead lies a planet full of unknown dangers. Now imagine the ship's controls are right in front of you. What would you choose? To die aboard the ship? Or to turn it around? Or perhaps Earth never existed at all, and everything is a lie. What would everyone else think? So you see, the generation ship must solve not only ecological problems, but also sociological ones. Over thousands of years, every possibility eventually becomes a certainty. The ship may never get very far before destroying itself from within.
Then why not just freeze people? Humans are always overthinking things. Sleeping sounds much safer.
Hibernation is indeed one of the more realistic options. Don't misunderstand me. I'm not saying cryogenic technology is easy. In fact, humanity has never successfully revived a human being from a frozen state. Frozen biological cells undergo vitrification, causing irreversible structural damage. However, compared with the concepts we discussed earlier, a cryogenic spacecraft would face relatively fewer challenges. A trip to Proxima Centauri would still take at least several hundred years. A hibernation technology capable of lasting that long is still essentially magic by today's standard. However, frozen sperm and egg cells already exist today. Build a nuclear-powered or light sail spacecraft operated entirely by AI robots, carrying human genetic information and artificial womb. Then, perhaps thousands of years later, human footprints would truly appear on a planet in the Proxima Centauri system. Considering the current pace of AI development, it might actually work. Of course, this is still the most optimistic scenario.
Even that is the most optimistic scenario. What have we forgotten?
Allow me to answer that, Master. You have overlooked humanity itself. The past half-century has been one of the most peaceful and prosperous periods in human history. Yet even so, national conflicts, religious conflicts, ideological conflicts, famines, and countless other problems continue to occur. Conflict and progress often go hand in hand, but nobody can clearly define the boundary between conflict and destruction. As technology advances, the threshold for civilization-ending weapons becomes lower and lower. One could even argue that the probability of another nuclear catastrophe occurring in the future approaches 100%. From a cosmic perspective, humanity's extinction may simply be a matter of time. If that is true, can humanity escape the solar system before it disappears? Or to put it another way, how far can Earth's civilization really go?
That is a depressing thought.
Actually, the ability to travel between stars is a way of measuring the level of a civilization. Think about it. Light sails, fusion engines, antimatter engines, stable closed artificial ecosystems. Once humanity masters these technologies, it essentially gains the ability to survive in space indefinitely. That means people from Earth could settle, live, and reproduce in space. For a species that evolved on Earth, that would be a form of evolution. A more likely future is that humanity expands through the solar system first. The new humans living in space would gradually spread farther and farther outward, just as ancient Homo sapiens once spread out from Africa. Throughout that process, the same old stories, wars and conflict, dictatorships and revolutions would continue to happen. Human social structures, ideologies, and technologies would slowly evolve into forms better suited to the age of space. And if we are fortunate enough not to destroy ourselves along the way, then sooner or later we will find it easy to accomplish things that seem almost like magic to people today. And that would certainly include the colonization of the Proxima Centauri system.